Okay, so in this chapter we talk about the access control models. So previously we mentioned access control matrix as an access control model, but it is a general model. To implement access control, the real-world system have different ways to manage the access privileges. So let's think about the example. If I'm the owner of a file, then can I set the permissions to access the file by myself? So usually you think that the answer should be yes, because I created the file. I'm the owner, so I can authorize whatever or whoever to access the contents of the file. So this policy or this model is called discretionary access control. So I'm saying the owner of the contents can authorize whoever to access he or she owns. That's one access control model. But in a different situation like military systems or some computer systems with very sensitive information, this model doesn't work. For example, if you have background clearance as maybe secret or top secret, you are authorizing somebody else to read a confidential file. So you may cause trouble depending on the authorized person's clearance level. So in a more secure system, we need to check the authorized person's clearance level or security level, and also the file security level being authorized. So that's a more secure system. So that we also call it the labeled system. So object and subject, they have security labels. So that would be a different model. And it's also considered as a more secure model. For such model, it's called mandatory access control. So we explain two types of access controls. So first, discretionary access control. In this category, the owner of object can determine who can access the object or how to access the object. So in a more secure system, it's called mandatory access control. So it's like even the owner cannot fully determine who can access the object that the owner created. Okay, so the system needs to follow some strict rules to determine the access. So as the two types of system. So discretionary access control is also called DAC, or mandatory access control is also called as MAC. So that's the basic idea of two types of access control systems. Now let's look at the more detailed models. So in this chapter, we focus on Bell-LaPadula model. This is mandatory access control model. So in the first chapter, when we provide the introduction to security, we mentioned the features of security. So confidentiality, integrity, availability, and accountability. So basically, the access control model it provides protection to the confidentiality. So the model says who can access what, or what permissions are allowed for the access. So the goal, we can say more specifically, we can say the goal of the model is prevent the unauthorized disclosure of information. So it's a kind of control of the information flow. Under this model, we usually we have many models, but the best known or well-known model is the bell-level Euler model. So it has multiple levels of secret labels in the system. Okay, this is the first step of the model. We consider 4 levels of security from the highest level to the lowest level. Will be top secret, confidential, and unclassified. So we can assign the secret level, secret levels to both object and subject. So a person can have a clearance level or security level at secret. A file may be at top secret or unclassified. So that's the security levels in the system. We also call it security labels. We label subject and object in the system. So more specifically, when we apply security labels to subject, we call it security clearance. When we assign the security levels or security labels to objects, we call it security classification. So in this example, we can see we have a column of subject and a column of object. So at each secret level, we have some subject and objects. So here you can see in this table, one subject can have only one secret level. It's the same thing for object. So we cannot put a subject at 2 levels. Okay. So here, after we assign the security levels, we can determine how to access object based on security levels. So here, a person at the top secret level can read all files. So just remember that the security policies are usually mapped or derived from real-world regulations, real-world policies. So here, this is reasonable to allow a top secret person to read low-level or the same level files. But you can see the second example. Query cannot read personal or email files. You can see a person at confidential level cannot read files marked at higher security levels. This is also reasonable. So here, a person at unclassified level can only read security levels at the same level, because unclassified is already the lowest level. So we are saying for read operation, if we look at the directions, so the top secret, secret, confidential, well, and unclassified. So you can read down. This is called read down. So higher level person can also always read something at a lower level. So here, if we go back to this slide, basically this slide say to determine the access permissions, we have to label all subject and object. Okay, so without a label, in this example, without a label, we cannot determine the access control permissions. So label is very important. So mandatory access control system is also called labeled security system. So more formal description is like this. So we allow the information flows up, not down. So read down, read down. So in the previous slide, read down. If we consider the information flow, it flows from the bottom to the top. That's the information flow. Okay. So basically, the access control rules determine how the information flows. So here we summarize as read up disallowed, reads down allowed. Okay, that's the simple security conditions first. So most formally specify that a rule is read as subject S can read object O if and only if the object security level is lower or equal to the subject security level. So a subject can always read files at the same level or files at the lower levels. So that's the rule. So this is called the no reads up rule, no reads up or reads down rule. So here, we actually mentioned the discretionary access control. So if two users are at the same level, theoretically, according to the no reads up rule, one person can read another person who is at the same level, file. But if we combine discretionary access control rule, so even if they're at the same security level, one person can set the file access permission to disallow others' access. Okay, so I'm saying two, Alice and Bob, they're all at secret level, but Alice can disallow Bob reading from Alice files. So this is the combination of discretionary access control and the mandatory access control. So in other words, when you apply, when you exercise your right of discretionary access control, you cannot break the rules of mandatory access control. So the DAC should abide by the restrictions of MAC. So that's rules. So now let's look at the right information. So previous step, we guaranteed that the information flows up, not down. So now we consider the right information. So we allow write up, but not write down. So if we allow writes up, the information still flows up. Okay. doesn't flow down. So that's because also got a star property. So this property specifies in what condition write will be allowed. So here, so if subject's secret level is lower than or equal to the object secret level, then the write permission will be allowed. This is reasonable because a lower level secret level person should be able to report to his or her manager. So we submit a report, then your manager may have higher security clearance. So it doesn't allow the information flowing down. Okay, so these two properties are combined together to be the basic rules for bell-labadula model. So there's no writes down rule. Okay. So to summarize the rules, we can say no reads up or no writes down. In other words, we can also say we can only allow reads down or write up. Okay, so that's the complete access control model. But this is the simple model. We later on will develop a more complex model, but the rules or basic idea is the same. So theoretically, we have proved, but of course we don't prove. We don't repeat the proof here. So the basic theorem is if a system initially in a secure state, and for every state transition, so like for any user activities that can cause system transition, for like such transitions, if we follow the two rules, no reads up, no writes down, then the next state of the system is still secure. Okay. So that's the basic idea for the bell-labadula model. So we can further develop the idea to more complex systems. So in the previous example, we only have clearance level or classification level assigned to the subject or object. But in the real world, we may assign categories to subjects and objects as well. So for example, in this example, the security levels are more complex than the previous example. So the security level has two parts, like here. So a security level can be top secret and also attached with a set of categories. So like categories, nuclear, Europe, or Asia. If it's a person, that says the person has security clearance at top secret level, and the person can access nuclear related information or any information related to Europe or Asia. If it's a file, it says this file is at top secret level, and the file has some information about the nuclear Europe or Asia. So similarly, we have other two examples: confidential level Europe, Asia, or secret level nuclear Asia. Okay. So now when we compare two security levels, we need to compare both parts of the security level specification. So here let's see the comparison of two levels. So if one level is higher than the other one, we say one level dominates the other level. So they may be at the same level. So we will say dominates another level. So the examples here, for the first example, we can see one level top secret. We compare the two parts. So top secret is higher than secret, right? So for the first part, we can see the previous the left level is higher than the right one. Then the second part, category. The first category, set of category includes nuclear. The second category is nuclear only. So when we look at the set of categories, the second set, okay, the second set is a subset of the first set of categories. So for this example, we can say the first security level dominates the second security level, because for the first part, left one is higher. For the second part, left one is a superset. Okay. So let's look at the second example. Secret is higher than confidential. Then if you look at the categories, they're the same. Okay. Then we can say the left secret level dominates the right secret level. So you look at the third part. Even though the left one is top secret, right one confidential, but when we look at the categories, the right one is not a subset of the left one. So they don't have any overlap. So none of the category is the superset of the other. So not dominate. So none of them dominates the other. Okay. So, or we can say not comparable. So now you can see we have more complicated case. Previously, for 4 secret levels, any two of them can be compared. But here we have situations that not comparable. Okay, if 2 security levels are not comparable, it happens in the real world. Then we don't allow any access. Okay. So if you recall, what we have learned in discrete mathematics. So the dominates, this is relation. Dominates is relation. So the security levels and the dominates relation can be considered as lattice. Okay. Considered lattice. So in the lattice, some security levels are not comparable, but some are comparable. Then we can determine the access control based on the based on the secret levels. So this is the so when you draw the figure, you can consider that you use graph to draw the lattice, and then you can see the 2 points of the lattice. So here, security labels are partially ordered. So partially ordered means not all secret levels are comparable. So some may be not comparable. So if we consider secret the relation dominant, but greater than, so in the simplest or in the first security model or linear secret levels, then greater than is the total ordering. So for any two levels, we can always compare them. So this is different. So now we have more complex case. We still follow the two rules we mentioned before. We only allow information flowing in one direction. So in other words, flows up, not down. So here we simply change the greater than to dominates relation. So if the subject secret level dominates the object secret level, we allow read permission. So please note we can also combine mandatory access control with the discretionary access control. Or this is the revised no read up rule. So similarly, if the object's secret level dominates the subject's secret level, then the read permission will be allowed. So this is called no writes down rules. So still the same, two rules, but we have more complex secret levels in this case, in the second case. So similarly, if a system starts from a secure state and we strictly follow the two rules mentioned before, then the system will finally reach a secure state. So if these two rules are followed, the system will maintain its secure state. So that's the good thing of the security. Secret levels. So now let's talk about the real-world system. So before we continue, so current operating systems, they don't use top secret or secret labels, but you can certainly use other labels. So you can try to view the examples in our last video. When we introduce access control matrix, I use a command. I use the command ls with command line option -z to display the security labels. You can check the video again, or if you have access to any Linux system, you can try ls with -z. But some systems, if you can see more security labels, then it has SE Linux installed. So SE Linux is developed by NSA. It has mandatory access control implemented. If your Linux system doesn't have SE Linux installed, it doesn't have mandatory access control. I mean, usually it doesn't have mandatory access control features. But to use the mandatory access control feature, you have to label. You have to label every subject and every object in the system. Then the access permissions can be determined. So that's how the real-world system implements the mandatory access control. If you want more detailed information, you can read more about E Linux developed by NSA, National Security Agency. Usually Fedora CentOS, so these two distributions have SE Linux installed. So you can try these two distributions of Linux. Okay, so now let's look at the problems of security labels. So so let's look at the two person here. So one person has secret and nuclear Europe. Nuclear Europe has category set. Another person has secret Europe has the category set. So one person dominates another one. Okay. But we have a problem here, because according to the rules we allow write up or read down. Okay. But not vice versa. So if two persons are at different secret levels, they cannot even communicate in two directions. So this will cause big problems. So you think about the two network system or two computers on the network. So if the two computers have different security labels, then how we can have a bidirectional communication channel established? So this is a big problem. So now let's look at the solution. So when we provide the first example of security labeling, I mentioned specifically, explicitly mentioned one subject has only one security label. Okay, so here we need to think about something different. So a subject may have multiple security levels. So one is the maximum level, one is the current level subject. So usually the max level should dominate the current level. In other words, I'm at the secret level, but I may downgrade my level to unclassified to do some work. So temporarily lower my security level. But of course, when I lower my secret level, I can only do work at the specific lower level. I cannot do any work assigned to higher security levels. Okay, otherwise I will break security rules. So here, so to solve the problem, we have to assign kernel two different levels. The maximum level is nuclear Europe, two categories, and the current level is set to secret Europe, so to be the same as the major. So if kernel can lower his or her level to a lower level, then they at the same as the major's level, so they don't have a problem to communicate. Okay. So that's the solution. So temporarily lower one person's security level.